I welcome you all the students of class 11th. Chapter 1 of your physics book is Units and Measurement. Let us learn this chapter in a systematic way. Let us start with the formal definition of physics. Physics is the scientific study of matter, its fundamental constituents, its motion and behavior through space and time, and the related entities of energy and force. In physics, we study about matter. Everything around you is matter, which has mass and which you can feel by your senses is matter. But what do we study in physics? We study the motion and behavior of this matter in space and time. And we also study the related entities such as energy and force. Basically, we study quantities, and especially the physical quantities. Quantity is the amount of substance. So any substance has amount, that amount is called quantity. And if we can measure the quantities, then those quantities are called physical quantities. Hence, physical quantities are measurable, such as length, time. We can measure length and time. Then we have mass, and there's so many physical quantities. Let us take few more quantities, such as force, pressure, area, etc. If we try to analyze the quantities, then we find quantities are related to one another. Sometimes length is related to time, or length is related to force. Force is related to pressure. Length is related to area, and so on. The work of physicists is to find or identify the quantities and then understand the relationship among quantities. These relationships are the laws of physics. To understand the laws of physics, or basically to know physics, we need to measure these physical quantities. Physical quantities are measured in units, such as the unit for length is meter, and the unit for time is second, the unit for mass is kilogram, and so on. Units are chosen and accepted basic amount of quantities used as comparison for measurement of physical quantities. First important thing is that units are chosen. So we choose units. We as in sometimes a society, a company, a country, or the whole world can choose a unit. Some of the popular systems of units until recently the world has seen are CGS, FPS, and MKS. CGS stands for centimeter, gram, and second. FPS is foot, pound, and second. And MKS stands for meter, kilogram, and second. All these three systems highlighted the measurement of three physical quantities especially. The first one is length, and then mass, and time. In the year 1971, one international body called the International Bureau of Weights and Measures, or BIPM in short, gave a list of physical quantities and they named them International System of Units. The most recent revision on this list was done in November 2018. Before I give you the list, let us understand the categories of physical quantities. Physical quantities can be divided into two types. One is called the fundamental or the base quantities, and the other one is the derived quantities. To express a particular fundamental or base quantity, we don't really need the help of any other physical quantity. In the case of derived quantities, we need to take help from other quantities for the definition of a derived quantity. For example, speed is a derived quantity And to express speed, we need to express it into two different quantities. The one is length and the other one is time. For speed and force respectively. And now we are in a position to say that the result of any measurement of physical quantities are expressed in two parts. The first is the numerical part, or N, and the second is the unit part, U. So if we measure the length, we have to write something as 10 meters. As it is obvious, 10 is the numerical part and M or meter is the unit part. The International System of Units, or the SI units, is a list of 7 base quantities along with 2 dimensionless quantities. Let me list it down with the name and the symbol of these quantities. So the first quantity is length. And length is measured in meter, that is the unit of the length. And the symbol for this unit is M. The second quantity is mass. The unit is kilogram and the symbol is kg. Then we have time. Time is measured in second and the symbol is S. Then we have electric current. Electric current is measured in ampere and the unit is capital A. Then we have thermodynamic temperature, and temperature is measured in Kelvin and the symbol is capital K. The sixth one is amount of substance and the unit is mole, M-O-L-E, and symbol that we use to represent this unit is M-O-L. And the seventh one is luminous intensity, and it is the amount of light, and we measure this in a unit called candela, very much related to candle, and the symbol is CD. We really don't need to mug up or cram up the definitions of these physical quantities or the units, but we just need to understand these quantities. In your book there is a list. In reference books you can go for a list. So you just have to go through the definition a couple of times just to understand it. Let me also write down 2 supplementary units. One is for the plane angle or the angle. This physical quantity is dimensionless and we measure plane angle or angle in SI units in radian. So radian is the SI unit for plane angle or angle. Let me show you the radian measure in the picture. So if delta theta is your radian measure, that is the measure of the angle, so delta theta is equal to the arc length, that is this length, and just name it S. So length of arc is S, and that has to be divided by the radius. So when we do that, when we divide arc length by radius, we get the value that is the measure of the angle in radian. The second dimensionless physical quantity is solid angle. It is a 3-dimensional angle, just like you're having a cone, ice cream cone. The cone you see, that has some angle. And we can say that delta omega is the solid angle, and it is equal to the surface area divided by the square of the radius of the sphere. We measure solid angle in a unit called steradian, and the symbol is SR. So the solid angle delta omega is actually the angle inscribed by the small area delta A, and this angle, just like a cone, is the solid angle. Normally, the reported result of measurement of a physical quantity is a number. Sometimes this number is a single digit number or a multi-digit number. And we also know every measurement involves error. Chance of errors can be reduced if we work on the precision of measurement. And that is why we have this topic called significant figures. As the name suggests, significant figures are the important figures, because one of the meanings of significant is important or something that can not be ignored. As we know, the result of measurement of physical quantities has two parts. One is the numerical part and then the units. For example, the period of oscillation of a simple pendulum is 1.62 seconds. In the numerical part, the last digit is called uncertain, and the first two digits are the certain or the reliable digits. The reliable digits plus the uncertain digit make the significant figures or the significant digits. In the given example, there are two certain digits and one uncertain digit. And in total, there are three significant digits. Let's take another example. The length of an object reported after measurement is 287.5 centimeters. Again, in this, the last one is the uncertain, and the first three are the certain or the reliable digits. And in total, there are four significant figures in this result. Why is the last digit called uncertain? Because we are not sure about the exactness of the last digit. It depends more on the kind of scale we are using. For example, to measure this length, on the scale there is a reading 287 and then 288. And our result 287.5 is somewhere in between 287 and 288. We can't say that 287.5 is the exact measurement. It can be 287.51 or 287.500001. Think about it. That's why we can say the last digit is uncertain in our significant figures. Obviously, there are rules to determine the significant figures. To start with the rules, let's take one example. Reported result of the measurement of length is 2.308 centimeters. Again, in this result, there are four significant figures. If the same result is written in some other units, for example, 0.02308 meters, 23.08 millimeters, and 23,080 micrometers. In all these results, the number of significant figures will not change. So for all these results, there are only four significant figures. For example, in meter, it is these four significant figures. And for millimeter, it is quite obvious what you can see. And for the micrometer result, the four significant figures are again 2, 3, 0, and 8. And we can say that a choice of change of different units does not change the number of significant figures in a measurement. And not choosing the last zero is part of the same plan. You can take this as the first rule in choosing significant figures. Here, non-zeros, zeros, location of the digit, and the decimals play an important role in choosing the number of significant figures. Let us see more rules. One is that all non-zero digits are significant. In the example 2.308 centimeters, obviously the non-zeros 2, 3 and 8 are significant. So non-zero digits are significant. Then we have all the zeros between non-zero digits are significant, irrespective of the presence of decimal. In the same example, 2.308 centimeters, 0 is placed in between two non-zero digits. That's why this 0 is significant. It doesn't matter the reported result has decimal or not. So for example, in 2308 centimeters, this 0 will be significant, just like in the case of 2.308. Next rule is, if the reported result is less than 1, then the zeros on the right of the decimal but to the left of the first non-zero digit are non-significant. We know that results like 0.3 meters or 0.3 meter means the same, and obviously this 0 is not significant. But what if the result is written something like 0.002308? The given result is less than 1, and here we can see this, the first 0 is not significant, and according to the rule these two zeros are also not significant. Why? Because these two zeros are on the right of the decimal and on the left of the first non-zero digits. So simply, if you see zeros are put before the first non-zero digits, these zeros are not significant. Let us see rules about trailing zeros, zeros that comes at the end of the result. The first rule is, the terminal or trailing zeros in a number without a decimal point are not significant. That's why in our example of 23,080 micrometers, the last 0 is not significant, because the terminal zeros are not significant if there is no decimal point in your answer. Let's take other example. In 123 meters, there are only 3 significant figures. The same result can be written in centimeters, that is 12,300 centimeters, or 1,23,000 millimeters. In all these 3 results, there are only 3 significant figures. Since, according to the rule, we have to ignore the trailing zeros. The rule says the trailing zeros in a number with a decimal point are significant. So in our examples 3.500 and 0.06900, in these two results the trailing zeros are significant, unlike in the previous examples. So in the result 3.500 there are 4 significant figures, and in the result 0.06900 there are 4 significant digits. Let us address a genuine confusion when finding the significant figures in which zeros are involved, the trailing zeros are involved, and the decimal is involved. Let us start with taking example, that is 4.700 meter, that is equal to 470.0 centimeters, that is equal to 4,700 millimeters, and finally that is equal to 0.004700 kilometers. It is the same quantity in 4 different units. Let us find out the significant figures of all these answers. In meters, there are 4 significant figures, 1, 2, 3, 4. Trailing zeros are also significant because decimal is involved. In the second example, 470.0 centimeter, there are 4 significant figures because decimal is involved, that's why trailing zeros are significant. But when we come to the third example, the problem arises. Here, there are 2 trailing zeros, no decimal is involved, that's why there are only 2 significant figures. And in the last result, in kilometers, there are 4 significant figures. Now, because of this confusion, we have to find a proper solution. Because what was the first rule I gave you? That changing the units doesn't affect the number of significant figures. But when we see the results here, these are the same values, but written in different units, and one has 4 significant figures, the next one has 4 significant figures, but the third one has only 2 significant figures. And to address this confusion, we can write our results in scientific notations. Scientific notation is the way to report every measurement in the power of 10. It is written something like A multiplied by 10 to the power B, where A is the number between 1 and 10, and B is any power or negative power or exponents of 10. So power or exponent of 10. Let's take all these 4 results. That was 4.700 meters, 470.0 centimeters, 4700 millimeters, and 0.004700 kilometers. Let us start with the second example, that is 470.0 centimeters. Now, this can be written in the scientific notation where we have to choose A. Now, what is A? A is a number between 1 and 10. So, in 470.0 centimeter, we can start with choosing 4.700. Why? Because we have to choose a number between 1 and 10. Now, to do that, what we did, we moved the decimal from one place to another. And we moved the decimal before 2 digits. And whenever we move the decimal left side, then the other part of this scientific notation, that is 10 to the power B, gets positive exponent. So B will become positive. So if we move 2 digits on the left, so power will be 2. And we will write the same unit centimeters. In the third example, 4,700 millimeter, it can be written in the same way as 4.700 because we have to choose A, which is between A and 1 and 10. Then it is multiplied by 10 to the power B. Here we move the decimal 3 digits on the left. So decimal is somewhere here, and we moved it and we put it somewhere here. So we have actually moved the decimal 3 digits on the left. So we will put our exponent as 3 and we will write the same unit. Using these powers of 10 is crucial. By doing this, we are not changing the result, right? Let us see the last one. In the last one, again, we have to choose A, that should be between 1 and 10. So it is again 4.700 and then 10 to the power B. But here we are moving the decimal on the right hand side. So decimal from here goes to somewhere here. That is right hand side after the 4th digit. So the power will be -4 and the same unit. And now it is so evident that all these numbers have the same significant figures, that is 1, 2, 3, and 4. So writing any number in scientific notation help us to get rid of this confusion of significant figures, and we actually write in a way that all the numbers are having the same number of significant figures. And in writing or in counting the significant figures, we ignore the exponent part. Also, one important thing is that the number B is the power of 10, and this is called the order of magnitude. Order of magnitude. Let us do the rules for arithmetic operations with significant figures. Arithmetic operations involved addition, multiplication, division, and subtraction. The first rule is, in multiplication or division, the final result should retain as many significant figures as there in the original number with the least significant figures. Let's see the example. To find the density, we have to divide mass by volume. And if a mass is given as 4.237 gram, it has 4 significant figures. And the volume is given 2.51 centimeter cube. It has only 3 significant figures. So our result has to retain the significant figures of the number with the least significant figures. So that is the result, the answer of this calculation, mass by volume, should have only 3 significant figures. And the answer is 1.69 gram centimeter minus 3. Though if we divide 4.237 by 2.51, you can use your calculator, the result is something like this, 1.68804781. But we will stick with the number of significant figures from the original number having the least significant figures, and that is 2.51. In this, there are only 3 significant figures, so our answer should also have only 3 significant figures. The second rule is about addition or subtraction. It is different from the rule of multiplication or division, where our focus was on the number of significant figures. So we chose the number with the least significant figures. But when we do addition or subtraction, our focus is on the decimal places. So rule says, in addition or subtraction, the final result should retain as many decimal places as there in the number with least decimal places. Let's take one example. If we have to subtract 0.307 meter and 0.304 meter, then our answer is 0.003 meter. Or in another example, if we have to add 436.32 gram with the 227.2 gram, our result is 663.5 gram. If you analyze the result, first you see these two numbers. The first number has 2 decimal places. The second number has only 1 decimal place. That's why we will stick with the number with least decimal place. And that's why our answer has only 1 decimal place. And we will stick with the least one. Though it looks like adding these two numbers has result something like 663.52 gram, but this is not the correct result according to the significant figures. Rounding off the uncertain digits. Let us learn this topic by examples. Suppose we are given one result, that is 2.746, and we are told either we round off this number up to 3 significant figures or up to 2 decimal places. As we can clearly see that the number has 4 significant figures, and we are asked to round it off to 3 significant figures. It doesn't mean that we will leave the last digit and we will write our result as 2.74. No, this is incorrect. We have to seriously analyze this number. The last digit that is uncertain is 6, and that is more than 5. In that case, we will add 1 extra digit to the second last digit. So if it is 4, we will do it 2.75. And this is the answer for rounding off the result to 3 significant digits. In case our reported result is 2.743, and then we have to round it off to 3 significant digits, then certainly the last digit is less than 5, so we will just stick with the first 3 digits. And this is the answer for rounding off this number to 3 significant figures. And for both the examples, rounding off to 2 decimal places will have the same result. Sometimes the reported result is something like 2.745. Since the last digit is just 5, so if we have to round it to 3 significant figures, we will choose only the first 3 digits, that is 2.74. And if the reported result is 2.735, then also the result is 2.74. So here we have to focus. If the second last digit is even number, then we will choose the first 3 digits. Actually, we will just leave the last one. But if the second last digit is the odd one, then we will add 1 to this odd number to make it even. That's why 2.74. Let us explore the rules for determining the uncertainty in the results of arithmetic calculations. Let us take one example. The length of a rectangle is given 16.2 and uncertainty of plus minus 0.1 centimeters. And the breadth is given 10.1 plus minus 0.1 centimeters. Our purpose is to find the area of the rectangle, that is length into breadth, with uncertainty. Here the uncertainties are given in quantity, and our job is to convert the uncertainty in percentage. To find the percentage of uncertainty, we have to divide uncertainty by measured value, and that has to be multiplied by 100. So for length, the uncertainty is 0.1 centimeter. That has to be divided by 16.2 centimeter and then multiplied by 100. And the value we get is 0.6%. And now we can write our length as 16.2 plus minus 0.6%. In the same way, the breadth can be written as 10.1 plus minus 1%. Now we are in a position to find the area. So area is L into B, so we will multiply 16.2 by 10.1, and then we will combine the uncertainties. To do that, we will simply do the plus minus and we will add both the uncertainties. So it is 0.6 plus 1%. Adding the uncertainties in this way is called combination of errors rule. So our calculation leads us to this value, that is 163.62 plus minus 1.6%. Since numbers in the question have only 3 significant figures, so our answer would include only 3 significant figures. So from the result 163.62, if we want to write it into 3 significant figures, we will write it as 164. Now we can write back the uncertainty percentage into the uncertainty amount, and 1.6% of 163.62 is equal to plus minus 2.6, and the unit for area is centimeter square. Since our final answer is a whole number, we will try to put our uncertainty also in the whole number. So the final result will be 164 plus minus 3 centimeter square. The fundamental or the base quantities are the 7 dimensions of physical world. The dimensions of physical quantities are written inside a square bracket. We read it as the dimension of the quantity. Here it is length. So the capital letter L represents the dimension of the physical quantity length. Please make a note of the dimensions of 7 base physical quantities. On the left hand side, it is written the dimensions, and on the right you can find the physical quantities. In the study of mechanics, we only focus on the top 3 dimensions, that is the dimensions of length, mass and time. And with the help of these 3, we can write the dimensions of many derived physical quantities. let's say velocity. Velocity is length, that is the distance, divided by time. So we can write the dimensions of length divided by the time, or we can write L t to the power minus 1, and finally we have to place the square brackets. Since mass is not involved in velocity, so we can raise the power of mass to 0, which has no meaning because anything raised to the power 0 is actually 1, and then we can write length and time to the power minus 1. This expression is called the dimensional formula. So m to the power 0, L to the power 1 and time raised to the power minus 1 is the dimensional formula for velocity or speed. When we equate this expression to the symbol of the physical quantity again in the square bracket, so here the physical quantity is velocity, then this whole expression is called dimensional equation. Now we are in a position to define dimensions. So dimensions of a physical quantity are the powers or exponents to which the base quantities are raised to represent that quantity. For example, the dimension for force is mass, length and time to the power minus 2. We can see the base quantities are raised to some powers or exponents to represent that physical quantity, that is force. Hence, dimensions of a physical quantity are the powers or exponents to which the base quantities are raised to represent that quantity. Let's analyze force. So force is mass multiplied by acceleration. For mass we can use capital M, and for acceleration it is length time to the power minus 2. So we can write force, the dimension of force, as M, L and T raised to the power minus 2. Let's take another example. Suppose volume is our physical quantity. So what is volume? Length multiplied by length and then again multiplied by length. So if we multiply the physical quantity length 3 times, we get a physical quantity, that is volume. Now if we have to write the dimensions of volume, we will start with writing m is raised to the power 0 because no mass is involved in the dimensions of volume, and then length is raised to the power 3 because it is multiplied 3 times, and then time again time to the power 0, and this is the dimension of volume. And as we mentioned earlier, this is the dimensional formula for volume, and if we equate this with the symbol of volume, then this whole expression is called the dimensional equation. Let us do the dimensional analysis and let's find out its applications. Dimensional analysis is extremely useful. That is why the scientists have been using dimensional analysis for mainly 2 purposes. The first one is to check the dimensional consistency of the equation, and the second one is to deduce relations among physical quantities. These 2 qualities have helped scientists to discover and invent new theories and new formulas. Let's do these one by one. So first is checking the dimensional consistency of equations. All equations have 2 parts. One is the left hand side and the other one is right hand side, and we have to make sure that left hand side is equal to the right hand side. Even before getting into complex calculations for the given equation, scientists have to make sure that the dimensions of the left hand side is equal to the dimensions of the right hand side in any given equation, and this is known as the dimensional consistency of any equation. Let's take one example. The SI unit for energy is joule, and that is equal to kilogram meter square per second square. There is a relation that total energy is equal to potential energy plus kinetic energy. We have to make sure that the dimension of potential energy and kinetic energy should be equal. Then only these two physical quantities can be added. And we can say that only those physical quantities can be added or subtracted if they have the same dimensions. This simple principle is called the principle of homogeneity of dimensions. Now let us come back to our example, in which we have to check the dimensions on the left hand side and on the right hand side. And by doing that, we have to check the dimensional consistency of the equation. Physical quantity on the left hand side is energy, and the dimension of energy can be easily drawn from the unit of the energy, which has mass element. So we can write m, and then meter square, the dimension can be written as length square, and for per second square, the dimension would be time raised to the power minus 2. So this is the dimension for energy. If we check the right hand side, we have potential energy and kinetic energy. The formula for potential energy is m, that is mass, into acceleration due to gravity multiplied by height, that is a kind of length in upward direction. So the dimension is m, and acceleration due to gravity is actually L t to the power minus 2. And again, height is simply L. So it is actually mass length square and time raised to the power minus 2. So for potential energy, the dimension we got is m L square t to the power minus 2. And the formula for kinetic energy is half mass into velocity square, and the dimensions are m, and for velocity it is L t to the power minus 1, and we will square it from the formula, and our dimension would be m L square t to the power minus 2. So for kinetic energy, we get the same dimension, that is m L square t to the power minus 2. And here we have plus sign. Now we can simply see that on the left hand side, the dimension is m L square and t to the power minus 2. On the right hand side, both the physical quantities, the potential energy and the kinetic energy, have the same dimensions, and that is equal to the dimension of the energy. So in this way, we can say there is dimensional consistency of the equation. On the right hand side, there are two different physical quantities, but since they have the same dimensions, we can confirm the homogeneity of dimension, or the principle of homogeneity of dimension. So this whole equation is consistent in terms of dimensions. Let me draw your attention to something really important here, but very easy to understand, that when we add or subtract two physical quantities, we have to make sure the dimensions of both the physical quantities are equal. But when we multiply or divide any two physical quantities, it is not important that the dimensions of the physical quantity should be equal. Let us do the second topic of dimensional analysis, that is deducing relation among physical quantities. This can be best understood by doing a proper question. The question I have taken is from your book, that is example 1.5. And the question says, consider a simple pendulum having a bob attached to a string. So it is something like, there is a string and a bob is attached to it, and then it oscillates under the action of the force of gravity. So what happens? It oscillates. It goes in a to and fro motion. So it goes left hand side and then it goes right hand side. Suppose that the period of oscillation of the simple pendulum depends on length, mass of the bob, so the mass of the bob is m, and acceleration due to gravity g. Then derive the expression for its time period using the method of dimension. So question really wants us to derive relation among physical quantities. Let's see what all physical quantities are mentioned here. One is the time period, the period of acceleration, and that is actually the time. And then we have length of the string, so one physical quantity is length, and then we have mass of the bob, so mass. So then we have length, mass, and gravity, acceleration due to gravity. So we have actually 4 physical quantities, and we have to actually deduce relation among these physical quantities. To really do that, we have to go back to the question. In the question it says that suppose the period of acceleration of the simple pendulum depends on its length, mass, and gravity. So we can write the time period depends upon length, acceleration due to gravity, and mass. And we read it as time period is proportional to the length, the acceleration due to gravity, and the mass. First step is to change the proportionality sign to proportionality constant. So T is equal to K. Instead of this proportionality sign, I've used a constant, is equal to L, G, and M. Now we don't know the nature of length, or what is the power on the length, or what is the power on acceleration due to gravity or on mass. For that, the step is just put powers such as A, B, or C on these physical quantities. And that right hand side is actually equal in the dimension of the time period. So this is what we have to deduce. Now let us write everything in dimensions. For time period, the dimension is only T, and on the right hand side, for the constant of proportionality K, there is no dimension, so we ignore that. But for everything else, for length, so length, the dimension is L, and then the power is given A, so we will keep the power A, and acceleration due to gravity is acceleration, and the dimension is L, T to the power minus 2, but there is a power B on this gravity, and M to the power C is actually dimension mass and the power C. If you analyze this equation, you find that there are only 3 kind of dimensions are used. One is the time, second one is length, and third one is mass. But on the left hand side, mass is raised to the power 0, time is raised to the power only 1, that is single t, and length again on the left hand side is raised to the power 0 because there is no length element on the left hand side, so it is only time period. But on the right hand side, what do we see? L is for the length here, then we have second L in gravity, so we have L to the power A, and then L to the power B, because here you can see the whole gravity is raised to the power B, so this L has power B. And if we see the time part, the time dimension on the right hand side, so time dimension is only with the dimension of the gravity, and it has power minus 2 inside and B outside, so total power on time is, dimension time is minus 2B, and that on mass is just C. Let's refine this equation. So on the left hand side it is M to the power 0 T and L to the power 0, and on the right hand side we can see on L the power is A plus B. As we are multiplying the dimensions, so the powers would get added, and that on time is minus 2B, and on the mass it is C. Since the dimensions on the left hand side and right hand side are equal, that's why we can equate the powers. To do that, let us start with the dimension of mass. On left hand side, the power on mass is 0, and this 0 is equal to the power on mass on right hand side, that is C. And the power on time on left hand side is 1, so 1, and on the right hand side it is minus 2b, so 1 is equal to minus 2b. From this we can find the value of b, that is minus 1 by 2. And for the dimension of length, on left hand side it is 0, and on right hand side the power on the dimension length is a plus b. So a plus b is equal to 0, and we can put the value of b as minus 1 by 2. So a minus 1 by 2 is equal to 0. That implies a is equal to 1 by 2. Using these values of a, b and c, what you can see, a is equal to 1 by 2, b is equal to minus 1 by 2, and c is equal to 0. We can substitute these values to our original equation, that is t is equal to k, L to the power a, g to the power b, and m to the power c. So now we can write t is equal to k, L to the power, the value of a is 1 by 2, so L to the power 1 by 2, and then g to the power b, and b is minus 1 by 2, and after that m to the power c, and our c is equal to 0. Since m to the power is equal to 1, so we don't have to use the dimension m here. We will only stick with k, L and g. So our time period is equal to k. Now the exponent 1 by 2 or minus 1 by 2 brings the quantity inside the root. So we will write under root L by g. G is in the denominator because the power on G is negative. That's why it is in the denominator. And L is the numerator because the power is positive. So this is the final relation between, or relation among, time period, length, acceleration due to gravity, and mass. Since mass has power 0, that's why the value of mass element is only 1 or unity, so we will ignore that. And this is your answer. Now here what is more important to know is that using the dimension method or dimensional analysis method, we cannot derive or find the value of k. So this is unknown using dimensional analysis method. By going through the steps what I have shown here, you can find the relation among physical quantities given in any questions. Do as many as more questions to become more confident. And students, that is the end of our chapter 1. Now I just request you guys to go through in the comments and also in the description section, where I will put links to do problems, questions, and if you have any confusion, now you can come back to me, raise your questions, and I will be very happy to answer anything if it is possible in due time. Thank you.